All right, let's continue with question 2. So when the reaction is complete, will the volume of carbon dioxide at the end of the second experiment be greater than, less than, or equal to the volume at the end of the first experiment, and then justify? So remember, the second experiment, this was the powdered solids, so they ground them into a powder, and the first experiment was the chunks, solid chunks. Now, we did this question earlier, so if we go back up here, we see that whether you have a powder or chunks, that will influence the rate of the reaction, but it will not necessarily influence the volume of product that I produce. So we need to go back in the question. There's a hint at the very start of the question. Now here's a little AP strategy for you. Let me erase some of this information here. You have to always go back and forth and look at, I know these questions are kind of wordy, so you have to go back and look at the question, highlight key things, find the information there, because there's a hint in 2A where it says a student combines equal masses of your first compound and your second compound. So equal masses means whether it was in chunks or a powder. So look at what it says here. The student performs a second experiment identical to the first, except that you're using powder, but you did not change the amount of reactant you have. So because my reactants are the same, then my products will be the same. And my products are based on the limiting reactant, but what I know first is that it will be equal. The volume of carbon dioxide will be equal, and the reasoning is because no matter if you use powder or solid chunks, you used the same quantity of reactant. Quantity of reactants is the same. So therefore, your product's moles and volume will also be the same, and that will be based on your limiting reactant. Now you can look at the AP answer key to see the detail of what they put to get the 1 point, but you have to say both. You have to say you'll get the equal amount because you have the same amount of reactants. So the product carbon dioxide moles and volume will not change. Okay, let's move on to the next one. I started writing some jot notes here. But it says here the student conducts additional trials of the experiment and produces the following data table. So I'm given grams or the mass of each reactant. I've actually gone ahead and just turned them into mole. I did some rough work, so I did that on my own. And then carbon dioxide product is also shown. So based on the student's data, identify the limiting reactant in trial 3 and justify your answer. Guys, there's different ways you can calculate the limiting reactant. I like to use a method called cycles. And if you've never seen this before, this is how it works. But of course, there are other ways to do this as well, including a ratio method. Okay, to find the cycles, what I do is I take the actual moles, which is this value up here for my first compound, and I divide it by the theoretical moles, which is the coefficient. And in this case, I get the same number. So I get 0.0133. We can say the unit is times or x. And what a cycles calculation means is, let me just change this for 1 second here. If I have this many moles of this compound, I would be able to run the reaction this many times. Okay, so let's do the same thing for my other reactant. What color was I using? Was it this one? So for the sodium hydrogen carbonate, the cycles equals my actual moles. So in trial 3, it's 0.01489 divided by the theoretical moles, or the ideal mole ratio. And, okay, sorry, I just need to calculate this for 1 second here. we get a cycles of 0.007445 times. So what this means is whatever number is the smaller cycles, that is your limiting reactant. So in this case, that would be this compound. What this means is my sodium hydrogen carbonate or sodium bicarbonate, it will run out first. It'll run the reaction with fewer cycles, so therefore my limiting reactant is NaHCO3 because it runs out first. Okay, so hopefully you understand my reasoning behind that. Again, you can do a different calculation and justify it differently, but I do like this method and I hope that makes sense. Let's solve one more before I do the next video. Okay, the reaction has a delta S, remember this is entropy, greater than 0. Using particle level reasoning, explain why the entropy increases as the reaction progresses. All right, so what I know here is that delta S is a positive, some sort of positive number, and the reaction is getting more disorderly. Reaction gets more. Okay, so I know this information, and again, you can look at the answer key on the AP website to get more detail, but why does it get more disorderly? Well, let me scroll all the way back and let's look at the chemical reaction. So I've started on the reactant side. I have 2 reactants, aqueous things. And on the product side, I've created 2, 4, 5. I've created 5 molecules, and 2 of which are a gas. So I've created more molecules or more products, which anytime I'm creating more things, that's more disorganized. And I'm also creating gases, which are gases, that they move around a lot. They collide, they fly around. And we know that from states of matter, gases are the most disorganized compared to liquids and solids. So because of these reasons, the entropy, it makes sense that it's positive. The reaction does get more disorderly because we have created gases, which are disorderly molecules. They fly around, and you can explain this in your own words. Products are gases which are disorderly, and we have created more products than reactants, or compared to reactants. Okay, so let's pause it there and we'll continue question 2 on the next video.